Okay, guys, let's start the recording. Okay, hi to everyone. Today we have the last lecture by Shen on post-Minkowski and gravity. It's also the last lecture on this school, so feel free to start whenever you want, Shen.
Okay, yeah, so thanks for coming for a very last lecture of the week. And so there's something I want to finish on last lecture's discussion, which is what diagrams do we want to include when we do this gravity computation. And for the full series side, one basic thing we usually do is we just do the soft Q counting. So the diagram has to be classical or iteration. So for example, we know we have to include diagrams like this, where we have the box, the triangle, and even at 2D, we have this type of diagram, etc. So the diagram that looks like iteration, but remember, this is just a naive power counting, so it could still contain this classical part. Okay, but this is not actually the entire answer. You in general, you have to refine it by inspecting the pole structure. In particular, we usually need 1 meter line, 1 meter propagator per loop. So you can show this. Oops, what happened? You can show this in the case of potential mode, and from the integration that we described, simply because from potential mode, the energy integral, the only thing that contains this energy is from the matter propagator, which is like E omega minus L. So that's the only chance you can localize the energy integral, otherwise you'll be scaleless. But I do believe this will actually host in general, even when you include other region. We can discuss why I believe that's the case. But you do need to use pole structure to know what diagrams are relevant classically. So let me give you other example. Okay, so by Q counting, we expect this bubble diagram doesn't contribute, because this one, for example, scale as G squared over Q, and this one scale as G squared Q to the 0. And likewise, diagram like this. But there are other type of diagrams that just look like classical or sometimes even iteration, but which in the end actually doesn't contribute. For example, this type of self-energy diagram. And also you can actually try to make this quantum-looking diagram classical in the soft Q counting by adding more iteration. So for example, this diagram. So for 2 loop, we have this as GQ Q to the 0, and this one actually have the same counting. And likewise, and this one actually have G squared over Q squared. Because if you count the number of propagators, it's the same counting as the iteration box diagram. So the Q counting itself is actually inconclusive or insufficient. So why these diagrams in the end they actually don't contribute? So first of all, if you look at these type of bubble diagram, it actually doesn't satisfy this rule from 1 meter line per loop, and that's why they don't contribute simply because this energy integral that will integrate to 0. And the reason also apply to this iteration diagram. So even though you add 1 more rung to make the classical counting look, to make the Q counting looks classical, but the do integration inside this bubble will actually kill the result. And the physics interpretation is that these actually bubble correspond to the running of G, the G Newton, which is a quantum effect. And therefore, we don't need to worry about this for classical dipole in the sense in here. And for diagram like this, and you can use Q counting, the more rigorous argument is that when you do the integral, on this gravitational momentum, remember we focus on the potential mode. It has to know about the relative distance r. But this one, it only has a propagator that depends on this L. It doesn't know about Q, the momentum transfer, and therefore it also integrates to 0. And the physical interpretation of this is that there's a contact term here. So it doesn't know about relative distance Q. And the last one, this one is probably the trickiest one, because if you look at the scaling or the integral, so it has a two-metric line, which you can, for the leading Q counting, we can turn into the linearized propagator for the matter, and also have the gravitron propagator here. So in this case, you can see that the integral is homogeneous in L, therefore it's also scaleless. So it's actually 0. The reason I say this is tricky because as long as you go to T-loop, you can make the same argument and the argument will still be true for the potential region, but the result is not true if I replace this cap with the radiation mode. And we can also discuss about this, but at least for the potential region, this integral is also scaleless, and therefore we can surround this diagram. Okay, so the structure, so the another comment on the higher order G structure. So for order G squared from the EFT amplitude, we have things like G squared over Q. In the iteration, we have the RR divergent integral, which goes like 1 over Q squared, and with the IR divergence 1 over epsilon. So even though when we do integral reduction, this one we could have a correction on Q squared, this quantum effect doesn't interfere with this IR divergence and give you something classical. The same thing is not true when you go to order G cube or at 2-loop level. So we have things like G cube over Q to epsilon over epsilon. So these are the classical contribution, for example, coming from this nasty triangle diagram. And for the IR divergence, the structure now becomes still one leading order is given by 1 over Q squared, and it's 2-loop, so it becomes 1 over epsilon squared. But now you can see that if I have a correction on this integral, I'll say order epsilon, order Q squared, then this term can actually interfere with the IR divergence integral. So we actually have a quote-unquote quantum in iteration interference. And this actually causes a lot of trouble in practice because depending on what you call this IR divergent integral, you actually affect this finite bar. And so therefore you have to be careful at order G cube and beyond that, how to make this IR divergent, how to have well-defined IR divergence integral. And that's a place where EFT is useful because it gives you a basis how to pick this IR divergent integral and make the finite part well-defined. Okay, so just some comment on the things I didn't have a chance to explain from last week. Any questions so far? Cool. So I decided that I'm probably gonna talk about something more fun for the last lecture. And so based on the lecture so far, you probably can understand maybe like 80% of the current research paper. So now I'm gonna switch gear and talk about something like more toward the current research. So we've been talking about the potential contribution. And so the question is, what does that physical really mean? So physically, the potential, they have the scaling as v comma vq times comma q, and they're obviously of shell. So it means that even though we have a lot of diagram with some intermediate graphtowns like this, for example, but this graphtown actually doesn't contribute to the cuts because for the physical state, we only have the two black holes, the two heavy scalars. So that means that the series actually has the elastic unitarity in the sense that the S matrix should be a exponential, which is just given by this two heavy black hole state. When we consider all the interaction is given by potential. So there are two different statements in the literature. One is the so-called iconal approximation. So the purpose of this iconal approximation, at least the standard one, is to resum all this entire tower of laser diagram. And at least the well-defined thing is here, the thing I'm going to talk about here is for the leading order 1/q² behavior, and want to resum these infinite class, these infinite diagrams from these laser intervals. Okay, so I'm not going to go through the general case, but I'm just going to discuss the simple box integral that we saw from last time. So recall that the tree-level amplitude and 1, we have the following structure. So it has a numerator entry, that's a function of s divided by q². So let me define the base from this. Which is simply the Fourier transform of the Montan space from this Montan transfer Q to a hyperparameter B. And crucially, this Fourier transform, so previously when we do the potential, the Fourier transform is 3-dimensional because they are off shell. But now we want to do Fourier transform on the transverse hyperparameter space, which is 2-dimensional. So we have this D-2 here. So it defines the leading order iconal phase. And for the one loop, if we look at just the iteration part, we have this result. Okay, so this is result from the box integral, and these prefactor correspond to the Jacobian when we cut over this, and you can make this manifest by integrating out this integrating out this Lx. So it's similar to the energy integral that we have. Except that we also have the same symmetry factor 2 factorial. And now let me just copy this one. Okay. And we have this 2-dimensional transverse integral for L transverse square Q minus L transverse square. So to make this more suggestive, let me write this as d squared L1 d squared L2 1 squared L2 squared delta Q minus L1 minus L2. So you can see that after we perform this LX integral, the result actually turn into the cut of the boundary box. And the L1, L2 correspond to these two T-channel exchange. So you can see that this is a convolution of L1, L2. In the convolution, after the Fourier transform becomes a product. So therefore, if we still plug in this the same Fourier transform, but for order G squared, you'll see that this thing actually factorizes into the following. And we basically have the tree level square. Okay, so this is simply the tree level iconal phase square with this symmetry factor. So you can see this pattern of exponentiation. And one way to prove this iconal approximation is just do the same exercise, but it's for all the higher loops. And we can resolve this entire class of data diagram. And crucially, what we use is the metric propagator. So originally we have the full quadratic propagator, but to do this iconal thing, we simplify this by taking a linear part, which is also a plane wave approximation. Okay. Now we have, so the statement is that if you do the same Fourier transform, but for the entire amplitude at order 1/2 squared, so we're not doing just for G, but the full amplitude, the result is actually this e to I chi minus 1 over I. Okay. And recall that this chi1 is the Fourier transform to impact parameter space for at the tree level, and the result is this one. And there's an IR divergence here because remember that the momentum space we have 1/q squared, and when you do a 2D Fourier transform, the result is IR divergent. And this one, of course, you can expand into 1/epsilon plus log b squared. And we can come back later to what's the physical meaning of this IR divergence. But now, given that we already resum this entire amplitude, and you can see that this is exponential, so that explains why all these the box integral to the leading iteration part, they're just redundant because they just saw this exponential. And you can do one more trick, which is now this iconal phase is in the interparameter space. So given this order resummation at 1/q squared, now we can Fourier transform back to the momentum space. So this is given by the Fourier transform from the interparameter differentiation that we just resolved. So I'll drop the constant here and just look at this phase part. So I have e to I chi 1 over b. And this 1/epsilon, they just turn to a local delta function. And so let me only take this log part. And let me also call this as a end of sigma just for simplicity. So I have b squared I and sigma DIQB Fourier two-dimensional Fourier transform. So what's the result from this Fourier transform for this power law behavior? So its result is simply the gamma function. It's proportional to this gamma function. Okay. And the well-known thing for the gamma function, if you look at numerator, is that this result actually has an additional pole when IM becomes -1, -2, etc. And what's n? This n, recall, is the tree-level numerator with this Jacobian. So that means we have the pole at some I plus 2i, etc., which is n3 divided by this Jacobian for m1, m2, square root sigma square -1. So in the center mass frame, it's more suggestive if I write the denominator as the following. You just say identity. Where this P is the momentum and infinity. Okay, but we want this entire thing, which is, so remember this is proportional to potential, and want this entire thing to be imaginary in order to have pole. So the only case you can have this pole is when this P infinity is imaginary. That means the E total is actually less than the total mass m1 plus m2. So what's the interpretation of this pole after we sum this entire data diagram? So result out to be this pole of course corresponds to the binding energy of this two-particle bound state. This is something similar to what people in dark matter talk about this summer field enhancement, and these pole correspond to the binding energy because the total energy is less than the total mass. So we can see that by resumming these type of data diagram, actually tell us a lot about not just scattering amplitude, but also give us a hint about the binding energy. Okay, this sounds great, but if you want to generalize this to higher order, because remember, the only thing we are resumming so far is this tree-level entry divided by q squared. That's the same we're resumming. Of course, now we already computed the amplitude on the non-trivial part at 1 dB, and we also have like 2 dB, etc. We want to know how do we use this information. But the resummation in this approach is actually difficult, and also the when we want to get the binding energy by doing this Fourier transform back to momentum space and inspect the pole structure from this gamma function, it's also difficult when you go to higher order. So that's why we need a different language for this exponentiation. Okay, any questions so far? Okay. So now I'm going to use a different language for describe this exponentiation. So I'll use elastic unitarity. And namely, I'll use the fact that the S matrix is unitary. So if I use S equal to the usual 1 plus identity plus IM, then this simply turn into the optical theorem. So two imaginary part is equal to the phase-space integral of the M and M star. And in terms of picture, this correspond to this one. And the imaginary part of the process. Oops. Yeah. And you have to integrate over the internal phase space. So that's just the usual optical theorem in any QFD textbook. So now let's look at this internal phase space integral. So of course, this is say if I call this P1 minus L, P2 plus L, it's literally just integrate over this one with the delta function P1 minus L square. And you can simplify this calculation if you're willing to take the, again, linearize this delta function. And when you do this delta function, you'll see that you get exactly the same cuts we have previously for this one-do box diagram. And you'll get exactly this same Jacobian. And the result, of course, after you localize this the matter propagators, you get a two-dimensional space for this transfer, momentum transfer. So if you're willing to do this plane wave approximation, then the result is proportional to 4 and 1 and 2, and the two-dimensional momentum transfer, which is exactly the kernel you got from the previous iconal approximation. But of course, phrasing in this language is better because now we know that we also get small the L squared correction coming from this functional delta function. So that gives us a way to correct this phase space integral with the order Q squared correction. And again, this will be not for one loop, but relevant for 2 loops or beyond. Okay, so that's one way to do this phase space integral by brute force. Another will define where this is already being explored in great details, and the idea is that we want to explore conserved quantities. And while the conserved quantities, of course, the energy is conserved, but on top of that, the spin is also conserved. So instead of just using plane waves, which are the eigen state of momentum, linear momentum, want to use a state that has well-defined quantum number, energy, and angular momentum. And this will help us to simplify this phase-space integral, because this phase-space integral should conserve, should preserve this conserved quantity. So in other words, this phase-space integral that should be diagonalized in the energy, which it already has, but also in the angular momentum space. And this fancy basis is actually simply the partial wave decomposition that you have in quantum mechanics. Okay, and for scalar 2, we're summing over j equal to 0 or 2, blah, 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 even j, simply because this is scalar. So this is the simply the Legendre polynomial, or the Gegenbauer polynomial when you go to higher dimension. And you can find out what's the optical theorem in terms of this partial wave decomposition. So you turn the t, the Mandelson t, into this Legendre polynomial, and the s is only in this the partial wave coefficient f sub j. And the optical theorem in this basis is given by imaginary power of j proportional to simply to fj squared. So there's some normalization prefactor, but the important part is that previously the optical theorem is in terms of this non-trivial phase-space integral. But now, since we diagonalize this phase-space integral in the partial wave basis, the optical theorem here is simply algebraic relation. And the solution to this partial wave to this unitarity is simply that Fj is proportional to e to I chi j e. Okay. And one crucial assumption here, and that's why this is related to potential, is that when you do the optical theorem, in principle, you have to add other terms because we could have things with more than just two particle state contribute to the optical theorem, because the rule is that you have to solve for all possible state. But you can control this by demanding that all the gravitons are in the potential mode, and therefore they don't correspond to physical intermediate state. And in that case, the amplitude, according to the optical theorem, is simply given by this relation in the partial wave basis, and the unitarity demands that this partial wave should exponentiate. Okay, so now we have this exponentiation. We can see that the amplitude now is summing over j, f of j, the Legendre polynomial. And the next statement I want to use is that we only consider this in the classical limit. That means j much greater than 1. And in this limit, the sum becomes approximately a integration. And let me plug in the constraint from the last unitarity. And finally, the polynomial at log j would have this structure. Okay, so this j, we only know the magnitude. So here you have plus or minus j correspond to this thing as this scattering is either clockwise or counterclockwise. So you have plus or minus. You can see that this you can combine these two, and for the exponent, we have this. Okay, so that's the result coming from solving the last unitarity and in the classical or log j limit. But since we discussed classical, we can also have an alternative picture for this, which is the amplitude is simply given by the path integral in the classical mechanics. And the result should be localized on the classical action, the one evaluated on the classical trajectory. So we can see that now we have a direct mapping between the amplitude and the classical action. So this what's this classical action? So the classical action is simply p dot dx minus h dt. Okay. And this is saying that, so simplify this, so they should equal. Okay. And the classical action, if we use the polar coordinate, so P is decomposed into the radial part plus the angular part. And using angular momentum, I can write this P theta as J over R. And remember that J is conserved, and as well as energy. So this one I can decompose into PR dr plus P theta d theta minus H dt. Sorry. P theta r dt dc. And this one I can turn into J d theta. But since the J and the H, which is the Hamiltonian, which is the total energy, they're conserved. So this integral is simply given by j theta minus e t plus this non-trivial part. And non-trivial part is given by this radial momentum integrate over your trajectory. And this object is called the radial action in classical mechanics. Okay, so why is this important? It's important because according to this classical action, we already, once we know this radial action, we can already fix other quantities. So for example, demanding that the classical action, the variation of respect to j is 0, that means that the scattering angle theta is equal to minus IR, the derivative of radial action with respect to angular momentum j. So we know that this gives us the angle. And likewise, the derivative with respect to energy give us the time t is plus IR derivative of IR with respect to energy. And what this t means is the so-called time delay or redshift. Okay. And the angle is probably obvious when you have a center mass. When you have a scattering, the angle is just what you have from the scattering. The time delay means that the time delay is something when you compare with a free particle, and because of the presence of the two-body potential, the total time would be different from the free particle case, and that's something also related to very popular topic now, the causality. Because for a reasonable gravitational theory, this time delay should be positive. If we have something that's time advanced, you can actually create non-causal behavior. So that can also place some constraint on this on the potential. And so, for example, the linear order G, we see that this iconal phase is given by this behavior. So now we can see that this leading divergence 1 by epsilon actually correspond to a R divergence in the time delay. And this 1 by epsilon correspond to the R divergence in 4 dimensions. Okay, and when you take a derivative of this iconal phase with respect to the angular momentum, so remember angular momentum is P times B, so d chi dj is d chi dB per P, and this actually gives you a finite part correspond to square. So this R divergence, it's only in terms of the time delay, but as a scattering angle in 4 dimensions, still well defined as it should be. Okay, so the important thing, the important lesson we learned here is that through this the partial wave, we know that the amplitude is initiate, and using a semi-classical picture, we know we can identify this phase with the classical action. But since we already match the angular part, so this iconal phase, or the phase we got from the amplitude, actually correspond to the radial action. So that means that the radial action can be mapped 1-to-1 to the amplitude. I should say the conservative part. Maybe there's a mapping for once you add this patient, but that part I don't know. Yeah, I don't know whether it's true or not. But the question is, how do we actually do this extraction? Because from the language I talk about, we have to turn this amplitude in a partial wave basis. But that's not always something simple to do. What we want to do is something like before, where if we write an ERT amplitude, we have some finite part plus the iteration, which is given by pole structure like this. And by this case where minus p squared, just to remind you. So this is p, this is k, which so in this basis we pick using EFT, we find out that the finite part corresponds to the impetus, or which is simply the classically the p of r squared minus p squared ordered by order g. So we want to do something similar here, which we want to write the EFT in some basis, and we want to cancel all these divergence and leave something that's IR finite. We want to pick a basis that's on target to this radial action. So it turned out that the basis you have to do this is quite simple. So using this k is p minus l, so you just need to pick this being the this linearized part, and there will be a small Q correction which will change your finite part, which turn this impetus into the radial action. Okay, so the way you can do this is either do this by first principle, which is plugging the EFT amplitude to optical theorem and calculate the so first you can see this by plugging to the optical theorem and do the phase space integral honestly. The second way to do this is purely coming from classical mechanics, which is because this is EFT, so this is only about classical mechanics, nothing fancy. So we know when we change the basis, we'll change this finite part. And because you know this finite part corresponds to the Hamiltonian, corresponds to impetus. And so when you change this finite part, you can also check whether this quantity is the radial action or not. And turn out it is, and you can check to quite high order in G. So from these two ways, you can see that we can actually target it. We can target on the amplitude using this basis and find out the radial action. Okay. So now, any questions so far? Okay, so now let me move on to the mass scaling. So another interesting thing is that so far we only talk about from amplitude approach, but there's actually a lot of things you can learn from GR. And in particular, if you take the leading mass ratio, this corresponds to the probe limit. And the motion of the particle, the per particle, is fully fixed by the geodesic equation. So given the structural black hole background, if I consider heavy scalar and light scalar. So I want to see that how do we know which part of the amplitude actually correspond to this probe limit and the order by order correction. So we want to do some counting on the mass scaling. So for example, if I have a matter vertex, matter graviton vertex, the leading term is given by m squared. So this is P1, then I have M1 squared for the leading term. And for the graviton vertex, it doesn't know about the mass, so the V is scaled as order 1 in terms of mass. On the other hand, for the propagator, is scale as 1 over p, so it goes by 1 over m. And similarly for a graviton propagator, it just scales 1 over q. So in terms of mass, it scales order. But the crucial thing is that this is, again, this is only for the leading order. If I consider this matter propagator, say this 1 plus L squared, if I expand to higher order, you'll see that it gives me 1 over m times the correction that scale as q over m. So the mass counting, when you go to higher order, you have to consider this type of correction. Okay, so now let's see how it works for simple cases. So for tree level, we only have this diagram. So the scaling for each vertices, each vertex just give me n1 squared, m2 squared. So for one loop, I have this leading triangle diagram. So 1, 2, and I have two m2 vertices. So I have this one and one vertex on n1, and I also have a propagator on this particle 2. So this is overall scaling, which give me n2 q on n1 squared. Okay, and likewise, when I flip the triangle, I'll get something n1 q m2 squared. The important case is the box case, which you already can see that you can embed this two triangle into this box. So the box should contain this two different type of mass scaling. And indeed, if you just count the leading order, I have n1 square square and 2 square square, the two matter propagator n1 and 2. So this would be n1 cube and 2 cube. Remember, this box is at the iteration level, so you have to consider correction from order q over n1 or order q over n2, which each of them give you these two triangle counting. And now let me go to two loop. So similar to before, we can consider this triangle diagram. So the result will be m2 squared cube and 1 squared over the two m2 propagators. So this will be m2 to the fourth and 1 squared. And similarly, you can consider contribution from this box diagram. So again, so let me skip the result. So I just say m2 6 coming from the vertices and the two 1 and 2 propagator. And again, just like the box case, which we have to consider the iteration. So here, I also have to consider the order q squared. I could have n1 squared, things like m2 and 1 or n2 squared. Okay. So what's the conclusion from all this counting? So if you combine all the results here, so you can see that the one loop part, which has n1 squared, m2 squared, and 1 plus m2, and from tree level, the classical result is actually just leading order in the mass ratio. So it means both tree level and one loop, they're fixed by the product limit or the structural background. So from hindsight, we actually don't have to do the one loop calculation, but just using the structural just basic equation. So just to summarize that for order G, this is n1 squared, m2 squared. For G squared, we have n1 squared, m2 squared, and we have this ratio. But for GQ, we have n1 squared and 2 squared. We could have a number with n1 squared and 2 squared, but we have independent part coming from this. Okay, so this leading term here given by the Pope limit or leading order in the mass ratio, sometimes also called zero order cell force. This term is a new part because that corresponds to the first order in the mass ratio. So people also call that first order cell force. So you can see that this is really a two-way communication because if I know the result in GR for this first order cell force correction, then you can actually make prediction for this two-loop computation without doing all the loop integrals that we just discussed. So this is also called 2T method that by Thibault Damour, Vini, Joe Rocco. Okay. And one more feature is that the Amplitude actually give you a very clean approach on this mass ratio. So we just saw that the Amplitude, we know the classical part is given by this mass ratio behavior. So this is the n finite plus dot dot dot. And we can actually convert this to the radial action just by using this formula. dt squared q and formula. So the mass behavior from this contribution to the radial action is very clear, and we know where exactly this mass behavior coming from. And later, when we convert this to the angle, which is just partial I, partial j, and these j in the infinite parameter space, we have the following. So we can also see that these the momentum in the center mass frame give you something non-trivial in the mass ratio. So that's actually one advantage of the Amplitude approach, which is make this mass counting manifest. Okay, so I'm getting toward the end of this lecture. So let me just skip the final slides, but discuss open questions. Because I think eventually this is a field that's moving very fast, and this talk would have been different a year ago from now on. So I'd like to discuss what are the open questions in this field. So I think the ultimate goal of this field is to solve two-body problem in GR. And we like to do this in a theoretical way. So at least that's the goal, the dream that I want to achieve here. And as usual, from the Amplitude approach, we are trying to collect data order by order in G. And hoping that with enough data, we can have some insight into how to solve these two problems in GR. So of course, one way we can do this is to say, I want to collect more and more data. So, and to do more computation. And that will require streamlined calculation in both the integrands and the integrals. So for the integrand, I would say, okay, the thing that still open is how do we clean up this iteration structure. So I would say that the approach that's available now is already very fine-tuned. We can already target to the radial action, but still in the intermediate process, we still keep those iteration. And it'd be great if you can fully clean that out, make it just classical from the get-go. And there's a recent paper, very interesting, by the primary group that seem to have made some progress on this direction. Another aspect is how to do integrals. And from order G cube or 2 loop, the integrals are the so-called canonical form, and results are from D log. But that's already not true at 3 loops, where we have elliptics. And who knows how complicated it will be once you go to 4 loops. But we do need very efficient method on doing this integrals. So since integration by part or differential equation can be actually quite helpful here. So that's on the brute force calculation. So I think important aspect is that we discussed Amplitudes approach in the connection to the so-called cell force or the expansion in the mass ratio. So in particular, for the Amplitude approach, this type of diagram that we compute, if you count the mass ratio, this is actually just given by the probe limit. So that means we can actually learn a lot from GR because this entire set of diagrams are actually predicted by the probe limit or the structural background. And for the future, it's not clear to me, which direction this could go, because either we can make some progress on the Amplitude side and provide some insight into the GR cell force, or it could be the opposite, where the cell force result, because it's supposed to be non-perturbative, it's order G. So maybe result here can also help us for the Amplitude approach. So the current state of art, at least from equation of motion, is that the 1SF is relatively well understood. However, for the second order cell force, the equation of motion, as I'm not an expert on this, but at least it seems still a lot to be understood. So maybe this is a place where the Amplitude approach can be useful, because for us, we're just doing brute force perturbation, but maybe we can see some structure from Amplitudes. Especially one thing in practice that will be helpful is that from these integrals, we can know what are the spatial function, and that will help the people from the GR community, the cell force, if they know the spatial function, maybe you could help them solving this equation motion. Okay, so that's about the cell force. Another important aspect, I think, is on dissipation, or including the radiation mode. So far, I only discussed about the result with intermediate potential graviton. Of course, once you have lossy, this system will radiate. So it's important to include this radiation mode when you go to high enough order. And it's actually not a very high order effect. So for example, the standard radiation reaction or the Bergstrom radiation reaction force start at 2.5 p.m. So in practice, these are actually important. And this is still, people just started looking at this. For example, this radiation reaction first show up at GQ, which actually resolve a puzzle on a log divergence. And when you go to higher order, there are actually more changes. For example, for order G to the force, we have this tail contribution, which would cause you some artificial R divergence when you do the potential calculation. And when you go to higher and higher order, we'll have more and more divergence from the overlap between potential and radiation. So it's important to find a way to clean up this, even though we already have a lot of tremendous progress in the post-Hamiltonian side. So that could be one thing that can be very helpful here for us to understand this patient in the PM approach. And this could be also an opportunity, because once you have these logs, you can think about how to resum the logs using RG. So people look at this for the post-Newtonian side, where they can push things to like 20 PMs. by resolving these laws. But it would be great to have some analog statement in this post-Minkowskian regime. Okay, I think I'm going over time now. I didn't realize that because it was silent. The last thing I want to say is, I'll probably say quickly just a minute, is that another important aspect is the black hole structure. So just stating the fact that the current black hole, it has a spin interaction. And from low energy point of view, we cannot fix this because it's a UV information coming from details of the current black hole. But interestingly, from Amplitudes approach, these correspond to nice high energy behavior from the this is first discovered by the massive spin RST by Guevara, Oshoff, Vines, Yuting, et al. And so that means the Amplitude approach can actually have some insight on the details of black hole structure. Another useful thing is that the so-called love number or the tidal deformation of the black holes. So people very recently just came up with a symmetry argument that it would be great if we can see some insight from the Amplitudes approach as well. The last thing is that there has been tremendous progress in this gravitational EFT using constraints from positivity and causality. So it would be great if we can use some of these to constrain the classical physics in GR. It could be hard, but I don't know, because people seem to make a lot of progress recently. So it's possible that we can also say something interesting about GR using fundamental particle physics. So I'll stop here, and I'm happy to take questions.
Okay, thanks, Shen. It was really clear. Thanks for the really nice lecture. Let's see if we have questions. Actually, maybe I can start with one.
Yeah.
So when you talk about this exponentiation and with the radial action, this is in the conservative sector. If you were to include the radiation, do you still expect to have the exponentiation of the amplitude, or to be somehow spoiled by radiation reaction effects?
Yeah, this is an excellent question. The short answer is I don't know. It's hard to tell because once you add radiation, one thing for sure is that even the classical part should include the imaginary contribution to the radial action. But that's just for the very leading part of the radiation contribution, like T loop, for example, like this type of thing. But imagine if I go to 3 loops where I can have things like two intermediate radiation, then I don't know whether this partial is exponential or not. Mm-hmm. It's like the square of the imaginary part. But then, yeah, I don't know whether it is exponential or not.
I see. Okay, I see there is a raised hand by Martinez. Go ahead.
Hi, thank you, Shen, for the nice lecture. And so I would like to ask you, do you think amplitudes can give us an insight to, for instance, non-perturbative mergers? As far as we know right now, we need numerical relativity, right? To be able to get like the merger of 2 black holes into a single one. Is there anybody like looking into this direction using amplitudes right now?
I'd say that would be the dream, but it could be quite challenging. One thing that can help us toward that direction is that when we collect the data order by order in G, if you're able to somehow resum this not only in velocity but also in G Newton, I don't know whether it corresponds to not really non-predictive region like merger, but at least that can help you to extrapolate to finite G. So more toward the merger phase. Of course, the challenge is really that when you have the merger, you do have to talk about the event horizon because you're really talking about two black holes. So that's the part I'm not sure about. And another approach close to this direction is when people apply the soft theorem, because it doesn't directly help with the merger phase, but if the system on the end settle down to some final state, and the soft theorem, they only care about initial and final state. So even though this when you talk about binary system and they merge into one and eventually become a single body, single black hole, but the soft theorem can still say something non-trivial because it only cares about the very initial and the very final state. So that's another thing that sort of toward this direction.
Thank you. And if I can ask another question, just give the tidal effects. I mean, where are they encoded? Are they encoded in the loops or are they encoded in a tree level diagram? Can you just briefly comment about it?
Excellent. Good. So, okay, let me start with for the PM approach, what's the tail effect. So the tail effect comes from if I have this type of say if I have this is a tree level radiation. But if I consider adding like one more internal graviton, this is like a one-do correction to this tree level emission. And already at this level, you can, so let me shrink this line into like this, which is like a multiple moment emit the graviton. And whenever I add this correction, this already induces a 1 over epsilon divergence. So the statement about tail effect is that when you have a rescattering of this thing, when this come back to your binary system, this is what people call the tail effect. So in the usual diagram, what you would have is you would have a contribution like this. Okay, and what is this 1 over epsilon divergence? This is really coming from when we split the region into potential plus radiation. So this tail effect, we saw that already when we do the pseudo computation using potential region alone, and this will give us a 1 over epsilon IR divergence. And if we could repeat the same calculation in the radiation, this will give us a 1 over epsilon UV divergence. And you should find that they should have exactly the same value. And you might complain, okay, this is UV, epsilon UV, and epsilon IR, they are really the same, but there's a well-defined procedure to solve this. And the reason is that in DIMRAC, we have scaleless integral that you could add, formally turning this epsilon IR into the epsilon UV. So maybe the physics intuition is that when we do this split the graviton into different regions, we don't have a good way to split them without causing divergence. So the way we do the splitting is that usually this will cause us divergence, but eventually when you add down all the possible regions, these divergence cancel. But okay, this is just for divergence. The important physics effect is that whenever you have divergence, you have loss. So what are the logs associated with this divergence? So for a potential loop, so if all these are potential, then you have 1 over epsilon divergence, and the scale you have is only the Q, the momentum transfer. So the only log you could have is log Q squared, and then just put the RG squared, mu squared here. However, the same thing is not true if you have radiation. So then put this radiation. So you can count how many loops are radiation, and given the 1 over epsilon here, the radiation, the natural scale associated with some radiation is the energy. So you have VQ. So for each radiation loop, it contributes to so for each loop we have -2 epsilon, and there are 2 radiation loops here, so we actually have 2. So that actually gives us a log, not just in terms of Q, but also in terms of velocity. So when you combine these two, the mu scale cancels, but the physical effect of this is that it gives you something that corresponds to log omega squared over Q squared. So that's the tail effect, because you can see that the log you have now depends on velocity. And when you convert this to the position space or the time domain, you'll see that this gives us a non-local in time action. Once you have once you do Fourier transform on these logs. So maybe just the short answer is that you don't see that at tree level. You see that when you do this pseudo computation.
Thanks. Many thanks for the good answer.
Okay, is there any other question?
Can I maybe ask another?
Go ahead.
So on the cell structure, we didn't like saw that, right? Can you also comment a bit?
Which
the
structure?
Like you know, the tidal effects, or absorption of gravitational radiation.
Yeah.
Yes.
So tidal deformation. Yeah, so from the EFT point of view, from the energy point of view, you can describe this tidal deformation by just adding operators. So in the second quantization language, this will be the operator correspond to phi square, r square type of operators. But the important question is that what are these coefficients? And that's the thing that from just pure the energy point of view, I cannot fix this. I have to ask, like, from the EFT point of view, I have to do the matching to the UV scale, which is actually the full Einstein equation that tells us what are these coefficients. So that's for tidal. And for things like absorption, yeah, that's something also not included in this formula, although there are works by Goldberg and Rothstein where they discuss a lot about how to treat absorption in this context. And so from Amplitude's point of view, it probably would need something like this, the curved black hole analog, which is we cannot fix the coefficient of this higher spin interaction, but there's some special property in the amplitudes, for example, the energy behavior that could be on the connection to curved black hole. So I don't know what the analog is for the tidal deformation or love number, but if there's something like this, then I respect some connection like the curved black hole and the energy behavior.
Great, thanks.
Okay, guys, since this is everything for the questions. So okay, we are approaching the end of the school. There will be the tutorials, of course, again, but I would like to make like, few remarks on what we have seen today. Now, maybe I don't know if the other organizers can, you know, if they are available, maybe open their screen or whatever. So